This is my geometry course. Today we're going to learn inductive and deductive reasoning, among other things. If you haven't done the homework completely and correctly from the last class, do that homework before watching this video. Now, we're going to start by talking about inductive reasoning. It's best to just give you an example rather than read that complicated definition. So example 1, this is inductive reasoning. My cat has hair. Your cat has hair. The next door neighbor's cat has hair. Therefore, all cats have hair. That's inductive reasoning. When you take specific examples and you come to a conclusion based on those specific examples, you find a pattern. The pattern is that these three cats, they all have hair. And then you come to a conclusion or make a prediction based on that limited information. Now it's limited because there's only three cats. If we could see all cats in the world, we'd know that there's actually hairless cats. So our conclusion in this example, you probably noticed if you've seen a hairless cat, that in this example our conclusion was actually wrong, but it's still inductive reasoning. It's still logical to conclude that, even though our conclusion was wrong in this case. Because, again, inductive reasoning uses limited information. So let's give another example. It rained yesterday. It rained today. Therefore, it will rain every day of the year. Now, that's another example where our conclusion was wrong, because I don't think there's anywhere in the world where it rains every single day. I mean, there may be somewhere in the world, but I don't think so. So in inductive reasoning, sometimes your conclusion can actually be wrong. So again, we're taking specific examples and trying to make a prediction or generalization based on those examples. Now let's give an example where our conclusion will be correct, or pretty much correct. Old Faithful, a geyser at Yellowstone National Park, is known to erupt many times per day since its discovery in 1870. Because this always has been true, it will continue to be true. So that's an example where the conclusion is a fairly good conclusion, because it is true that Old Faithful is still erupting many times per day, and it's been that way since its discovery in 1870. Now, notice that we're coming up with conclusions or predictions using inductive reasoning for each one of these examples. There's a fancy term for that conclusion that we come up with, and it's called a conjecture. Each one of those conclusions is a conjecture. All cats have hair is a conjecture. It's going to rain every day of the year. That's a conjecture. Old Faithful will continue to erupt multiple times per day. That's a conjecture. So it's a conjecture. It's a conclusion based on inductive reasoning. So let's do some practice problems. In the following problems, make a conjecture based on the information given. So Bella likes to play the piano, the guitar, and the drums. Can you make a conjecture, a conclusion about Bella based on that information? Conclusions may vary a little bit, but see if you can come up with something. Pause the video, and when you come back, we'll do it together. All right, we're back. My conjecture is that Bella likes to play instruments. Now, this may not be true. It may be that she's being forced to play instruments. Maybe she comes from a musical family. Her parents are musicians and they're forcing her to play. Maybe she doesn't like to play instruments. But because she's playing so many different instruments, there's a good bet that she likes to play instruments. That's a conjecture based on the information given. So if your conjecture was somewhat like mine, then good job. Again, this is inductive reasoning. We're using specific examples in a pattern to come up with a conjecture, which is a conclusion or a prediction about the information provided. So let's try number 2. Last year, Larry's tomato plant didn't produce tomatoes, nor did it produce tomatoes this year. Make a conjecture about Larry's tomato plants. Pause the video. When you come back, we'll do it together. All right, we're back. The conjecture I'm going to make is that Larry's tomato plant will not produce tomatoes it just won't produce tomatoes. I guess we can just stop there. And by the way, we need to rectangle these. These are answers. So if you came up with something like that, good job. Again, these are just conjectures. Actually, that didn't make much sense, did it? I forgot to write the word produce. Produce tomatoes. So if you came up with something similar to that, good job. Now try number 3. Lions, leopards, and cheetahs eat meat. See if you can come up with some sort of conjecture based on that information. Pause the video. When you come back, we'll do it together. All right, we're back. Cats. I'm going to say all cats eat meat. Now again, that may not be true. None of these conjectures may be true. You know, sometimes you hear the word conjecture in a negative light. For example, you might hear somebody defending themselves saying, well, that's just conjecture. They're just coming up with conjecture. That's because conjecture is it's a weak conclusion in many cases because it's not proof. The limited information is not proof because it's based on inductive reasoning, limited information. But it's still logical to conclude that all cats do eat meat. All right. So if you came up with something like all cats eat meat, good job. All right, so now this is obviously a math course, so we're now going to go to numbers. So consider the sequence 1, 2, 4, 8. Use inductive reasoning to make a conjecture about the 5th number in the sequence. So we have limited information. By the way, these 3 dots here, that means that the numbers just keep going on and on and on. So we want to know what the next number is going to be. We don't have any clue what it's going to be, but we can use the limited information and find a pattern to see if we can come up with that 5th number. So pause the video and see if you can figure out what that 5th number would be. All right, we're back. If you saw a pattern here, there is a pattern. If we multiply 1 by 2, we get 2. And if you multiply 2 by 2, you get 4. And if you multiply 4 by 2, you get 8. So as you can see, we're just multiplying the previous number by 2 to get the next number. So now if you multiply 8 by 2, you should get 16. So 16 is the answer. That's the conjecture. My conjecture is that 16 is the next number, and I base that on a pattern. That's inductive reasoning with numbers. See if you can do, so anyway, good job if you got 16. Now see if you can do example 5. Consider the polygons below, make a conjecture about the 4th polygon. So try to find a pattern there and see if you can figure out what the next one's going to be. Pause the video. When you come back, we'll do it together. All right, we're back. So you have a 3-sided polygon, a 4-sided polygon, and a 5-sided polygon. So obviously, what is the next polygon going to be? Well, it's going to be a 6-sided polygon. So something like this. So if you said a 6-sided polygon, good job. Again, that's inductive reasoning, and this is my conjecture. My conjectures is going to be a 6-sided polygon. That's going to be the next thing in the list. Again, remember these 3 dots mean that you're going on and on and on for, and many more polygons in the list. All right, so on to number 4. Make a conjecture about the next thing in the sequence. So see if you can do number 4, and when you come back, we'll do it together. All right, we're back. You can see that we're just adding 2 for each one of these. So the next term is going to be 9. Because if you add 2 to 7, you get 9. See if you can do number 5, and when you come back, we'll do it together. All right, we're back. Now there's 2 things happening here. You're adding a segment for each symbol here, but you're also rotating it. So this one is vertical, these are horizontal, and these are vertical. So the next ones are going to be horizontal. At least that's our conjecture. And we're adding a line, so we have 3 lines here. So if you add one more line, we'll get 4 lines. Again, this is inductive reasoning. We're looking at a pattern and coming up with conjecture, a conclusion or a prediction about what the next pattern the next thing will be. All right, so if you got something like 5, good job. Let's try number 6. Pause the video. When you come back, we'll do it together. All right, we're back. So we're actually subtracting 50 each time. 50 minus 50 is 0. And then 0 minus 50 is negative 50. And if we subtract 50 from negative 50, we should get negative 100. All right? So if you got negative 100, good job. All right, number 7. See if you can do number 7, and when you come back, we'll do it together. All right, we're back. So the green hemisphere, or semicircle, the green semicircle is on the right of the square, and then it goes to the top, and it goes to the left. So based on that pattern, I'm going to make a conjecture. I'm going to try to draw it just like those squares. My conjecture is it's going to end up on the bottom now. Again, we don't know for sure, but it's a pretty good conjecture based on the pattern. So if you got something like that, good job. And make sure to rectangle your answers. All right, do number 8, and when you come back, we'll try it together. All right, we're back. So we're using letters, and these letters are alphabetical, except they're skipping. So if you had, if this one seemed a little more challenging, you're correct. We have, let's sing the alphabet here, not sing it, but let's just say it. A, B, C, D, E, F. So E, F, G, H, I, J. You see how it's skipping? So A, B, C, D, E. Let's see here. A, B, C, D, E, F, G, H, I, J, K. So it looks like the next one's going to be K. We're just skipping letters in the alphabet. That's the pattern. So that one was a little harder. So if you had a little trouble with that, don't worry about it. Some of these do get fairly challenging. All right. Let's see here. Let me move this down real quick so I can get more room. All right, try number 9, and when you come back, we'll do it together. All right, we're back. So this one seems pretty easy. Looks like it's just going to be 4 of these. That's not a very good picture there. But if you got that, good job. It's something like that. Seems like it's actually getting smaller, but whatever. All right, so like I said, some of these are more difficult. So these are going to be a little more challenging, but see if you can do them. I'm not going to give you really difficult patterns or sequences, but some of these, they're kind of interesting. So if you can get these, that's good, but if you have trouble, don't worry about it. Just try your best, and when you come back, we'll do number 10 together. All right, we're back. So if you notice something about perfect squares, this number here is 1 squared. 4 is 2 squared. 9 is 3 squared. And 16 is 4 squared. Now again, if you didn't see that pattern, that's okay. When I first looked at this stuff, when I was learning geometry, I didn't see this pattern either. So it's sometimes high school students and even college students have trouble seeing that pattern. You really have to know your perfect squares. But that's what's going on here. So the next term is going to be 5 squared. So it looks like the next term is going to be 25. Again, don't worry about it if you didn't get that one. It's okay. I just want you to see that some of the patterns, they get more difficult. See if you can find the pattern in number 11, and when you come back, we'll do it together. All right, we're back. So it looks like we're subtracting 1 to go from 10 to 9. Then we're subtracting 2 to go 9 to 7. Then we're subtracting 3 to go 7 to 4. And we should be subtracting 4 to go to 0. So our conjecture for the next term is going to be 0. So if you got 0, good job. All right. If you didn't get 0, that's okay. It's not a big deal. The most important thing is that you understand inductive reasoning. So try number 12. Again, number 12 is going to be challenging. So again, if you don't get it, that's okay, but just try your best, and when you come back, we'll do number 12 together. All right, we're back. So the easy part is that this segment is kind of just going back and forth, back and forth. That's not really the hard part. The hard part is the circles. So we have 2 circles, and then we subtract 1. Then we add 2 to get 3. Then we subtract 1 again. Then we add 2 again to get 4. So do you see what's going on here? We're subtracting 1, adding 2, subtracting 1, adding 2. Do you see that? Again, this is a more difficult pattern, so if you're having trouble with these, that's okay. Subtract 1, add 2, subtract 1, add 2. So the next symbol is going to be slanted to the left, and it's going to be 3 of these dots, or 3 of these circles. So I actually didn't think about where exactly you should put the circles. So in this particular example, I'm sorry about that. I didn't mean to really put any emphasis on where to put the circles. I probably should have thought about that more, but as long as you have a segment going from to the top to the bottom, left to right, and you have 3 circles, and that's all we're really looking for here. All right, so good job if you got that. And number 13. 13 is going to be a little bit more difficult here than the first ones we did. So try number 13, and when you come back, we'll do it together. All right, we're back. So what's going on here is you're actually multiplying by 1/3. 5 times 1/3. Remember, you put 5 over 1, then you multiply 5 times 1 is 5, and 1 times 3 is 3. So you get 5/3. And then you take 5/3, the second term, and you multiply that by 5/9. Or excuse me, you multiply it by 5/3 again. Or excuse me, multiply it by 1/3. 5 times 1 is 5, and 3 times 3 is 9. So you're multiplying by 1/3 every time. 5 times 1/3 gives you 5/3, and then 5/3 times 1/3 gives you 5/9, and so on and so forth. So we need to multiply 5/9 times 1/3, and we'll get 5 over 27. So I'm sorry if I confused you there, but again, we're just multiplying by 1/3 each time. So if you got 5 over 27, good. That was a challenge problem. All right, try number 14. And when you come back, we'll do it together. All right, if you said the next term is 16, you're correct. That was similar to one that we did previously. You're just multiplying by 2 each time. All right, number 15, go ahead and try that, and when you come back, we'll do it together. All right, we're back. So we have A, B, C, D, E, F. So it looks like it's alphabetical. That part seems pretty easy. So A, B, C, D, E, F, G, H. So G, H. And then we have 3, and then we're adding 5 to get to 8. And then we're adding 5 again to get to 13. So we need to add 5 again, and we have 18. So GH 18 is going to be the answer there. So if you got that, good job. All right. Complete the conjecture based on the following information. So we have some information here, and it wants you to complete this conjecture. So we have a empty space here. We need to figure out what this word is going to be. So we'll do these first two together. So you see this information here, and we have this clue here. The sum of two even integers is what? So the sum of two even integers is always equal to what? What is common to all these numbers? Well, if you said that they are even, you're correct. So we're just going to put the word even in there. So we're done with that one. All right. So if I did that too quickly, don't worry. I'm going to give you number 18 and number 19 to do on your own. Maybe you can try number 17, actually. I think you get the point. So try number 17. Make a conjecture based on the following information. So fill in this word here. When you come back, we'll do it together. All right, we're back. So the product of two odd integers is what? What's common to all these? Well, they're odd. So if you said odd, good job. All right, number 18, go ahead and try number 18, and when you come back, we'll do it together. All right, we're back. The sum of an odd integer and an even integer is odd. All of those sums are odd. So if you said odd, good job. Number 19, go ahead and try that one, and when you come back, we'll do it together. All right, we're back. The product of an odd integer and an even integer is even. If you said even, good job. All right, so that's inductive reasoning. We're using information. This is limited information. We're not multiplying, and by the way, I should have mentioned that, we're not multiplying every single odd number with every single even number. We don't have time to do that. We're just taking limited information and coming up with a conjecture that if we do this for every even and odd number, then our product is always going to be even. So that's the same situation with all of this stuff. We're just using very limited information and coming up with a generalization. That's inductive reasoning, using specific examples and coming up with a generalization. All right, so now we're going on to a counterexamples. A counterexample is an example that disproves a conjecture. So you might come up with the conjecture. For example, we already came up with the counterexample. There are some cats that are hairless. Okay, that disproves this conjecture that all cats have hair. There may be a day where it doesn't rain. That disproves this conjecture that it's going to rain every day of the year. If Old Faithful stops erupting, then that's a counterexample that disproves this conjecture that Old Faithful will continue to erupt multiple times per day. So a counterexample disproves conjecture. So see if you can find a counterexample for the following statement. All cars use gasoline. So that's a conjecture. Pause the video, see if you can come up with a counterexample. All right, we're back. A counterexample is some cars use electricity. They're electric cars. So if you got that one, good job. I know that cars run on other things also, but electric cars, that's the first example that I thought of. You might think of another example if you're interested in engineering and whatnot. So that's a counterexample. That disproves this. Not all cars run on gasoline. Some of them run on electricity. All right, so see if you can come up with a counterexample for number 21, and when you come back, we'll do it together. All right, we're back. The product of two positive numbers is always positive. So it is true that 2 times 3, those are two positive numbers, and the product is positive. It's also true that -2 times -3, that's going to be positive. So if you multiply two negative numbers, that's going to be positive. But it's not true that if you multiply a negative number and a positive number, that's going to be positive. That's not going to be positive. That's going to be negative. So this is one example of a counter example, because it's the product of two numbers and it's a negative. So we disprove that conjecture. All right, try number 22. Pause the video, and when you come back, we'll do it together. All right, we're back. So what if we add 8/9 and 8/9? Then we'll get 16/9. And if we change that to a mixed number, and you learned how to do this in my arithmetic course, so if you're a little rusty on it, that's okay. 9 goes into 16 one time. 16 minus 9 is 7. That's the remainder. And you write 9 and the denominator. So 1 7/9 is bigger than 1 1/2, as you might imagine. So that's an example of that's a counterexample. That disproves that statement or that conjecture. Try 23. When you come back, we'll do it together. All right, we're back. So some parakeets are probably the most common color other than green is actually blue. Some parakeets are blue. Some of them are white, albino. Some are yellow, what they call Lutino parakeets. That's just the names that the breeders use. There's others called harlequins. There's all kinds of different colors for parakeets. So if you got something along those lines, good job. Again, we're coming up with counterexamples to disprove these conjectures. Try 24, and when you come back, and you might want to look up the definition of prime numbers. We talked about that in some of my previous courses. Make sure you understand what all the prime numbers are before you do number 24, because you might get tricked. So do number 24, and when you come back, we'll do it together. All right, we're back. All prime numbers are odd. So it is true that almost every single prime number is odd. 3 is odd, 5 is odd, 7 is odd, 11 is odd, 13 is odd. I mean, these are all odd prime numbers, but there's one prime number that is not odd, and that is 2. A lot of people are kind of surprised to find out that 2 is a prime number, but it's actually defined to be a prime number. All right, so we disproved that statement because 2 is not odd. Try number 25. When you come back, we'll do it together. All right, we're back. So x squared is always greater than x if x is any real number. So let's say that x is equal to 2. Actually, let's say 3. If x is equal to 3, then obviously 3 squared is greater than 3. Okay, so x squared in that case is greater than x. X squared is greater than x. Remember these inequality symbols. X squared is greater than x. Remember, Pac-Man wants to eat the bigger one. So that's all that means. So in this case, if x is 3, you can see that that's true because 3 squared is 9. 9 is bigger than 3. So we have to think of an example where it doesn't work. What about a negative number? Let's say that x equals negative 3. Let's plug that in. So negative 3 squared, let's see if that's greater than negative 3. Well, if you continue here, we see negative 3 squared is positive 9, and that's still greater than negative 3. So we haven't come up with a counterexample yet. So let's see here. What about a fraction? What if x equals 1/2? And we're going to find out that that's the ticket right there. X equals 1/2. So 1/2 squared, let's see if that's greater than 1/2. So if you square 1/2, you get 1/4, and 1/4 is not greater than 1/2. So that was an example where x, it didn't work. So in case you're wondering what a real number is, that all the numbers that we've worked with so far, those are all real numbers. So this is a counterexample to that when you use a fraction. All right, so 26. I'm gonna do 26 with you because 26 is a little weird. So this is a conjecture, and we're going to disprove it. So we're going to use x equals 1 and x equals or y equals 2. That should work. So now let's plug in 1 and 2. So square root 1 plus 2 is equal to square root 1 plus square root 2. I'm going to just say not equal to because I'm pretty sure it's not going to work. And then we get square root 3 is equal to square root 1 is 1. The square root of 1 is just 1. And square root 2 is whatever that is, but these are not equal. These are definitely not equal. If you actually plug these into the calculator, you'll see that they're not even close. So that's one example. You could use a lot of other examples too. But I just wanted to do that one with you so you could see how those work because we haven't done one of those yet. All right, number 27. Pause the video. When you come back, we'll do it together. All right, we're back. All meat comes from cows. What's a counterexample of that? Well, if you said some people eat, I don't know, deer. Let's just say deer. If you said some people eat deer, then that's a good example. You could have come up with many, many other examples. All meat does not come from cows, so we came up with a counterexample. So if you came up with something like that, good job. All right, now we're going on to conditional statements. A conditional statement is usually written in if-then form, and it's written if X, then Y. For example, you might say, if you come to the movies with me, I'll buy you popcorn. That's a conditional statement. If you come to the movies with me, I'll buy you popcorn. The part after if is called the hypothesis, and the part after then is called the conclusion. That's just the fancy names that they give those parts. So let's give an example of if-then conditional statements. If it rains, then I will take my umbrella. That's another example. I guess I already gave you one with the movies. So now let's do some practice problems. Write the following statements in if-then form. 3x plus 6 equals 15 because x plus 3, or x equals 3. So let's write that in if-then form. If 3x plus 6 is equal to 15, comma, then x is equal to 3. Does that make sense? So we took this statement and we just turned it into if-then form. If-then form is a much more powerful way to say that. So we're just getting used to using if-then form because, again, if-then form is a very effective way to make a statement, a conditional statement. So see if you can do number 29, and when you come back, we'll do it together. All right, we're back. Let's see here. If a creature, I'm just going to call it a creature because I don't want to call it an animal because I'm not sure that turtles are in the animal family. If a creature is a turtle, then it has a shell. So it's now an if-then. It's now an if-then form. You see the if and the then? If and then. If a creature is a turtle, then it has a shell. So if you got something like that, good job. Whoops, my computer's running a little slow here. Sorry about that. All right, let's do some more of these problems. See if you can convert this statement to if-then form, and when you come back, we'll do it together. All right, we're back. We learned about vertical angles in a previous class in this course. If two angles are vertical, then they are congruent. So if you got something like that, good job. Again, we're changing these statements to if-then form. All right, try number 31, and when you come back, we'll do it together. All right. If a polygon has congruent sides, then it is equilateral. And we talked about equilateral polygons, I believe, in the last class, if I remember correctly. So you should be fairly familiar with that terminology. All right, so if you came up with something like that, good job. Try number 32. When you come back, we'll do it together. Oh, wait a second. Identify the hypotheses and conclusions in the previous 4 problems. All right, so let's actually do the first couple of these. So we're going to identify the hypotheses and conclusions. So this comes before if, so it's the hypothesis, and x equals 3 is the conclusion. So for number 28, that was 28. I'm going to write these down. So for 28, the hypothesis was 3x plus 6 equals 15. So I'm just going to say H for hypothesis. And conclusion was x equals 3. And hypothesis is a creature is a turtle. And conclusion is it has a shell. And so now I want you to try number 30 and 31. What is the hypothesis for 30? The hypothesis is two angles are vertical. If you got that answer, good job. Now what is the conclusion? The conclusion is they are congruent. I'm not going to write out every detail of the sentence. I think you can get the point. All right, so if you got that, good job. Number 31, try 31, and when you come back, we'll do it together. Identify the hypothesis and the conclusion. All right, we're back. The hypothesis is a polygon has congruent sides, and the conclusion is it's equilateral. So if you got those answers, good job. And I want to rectangle that whole thing. All right. So now we're going to talk about negation. Negation is the opposite of an original statement. So, for example, you might have a statement, the flowers are red. If you negate that statement, you say the flowers are not red. All right? So pretty easy. Now, sometimes you'll start out with the number is not even. If you want to negate it, then you take away the not. So just be aware that sometimes you start with not even, and then you take away the not to negate it. I didn't give you a lot of those problems. I think I maybe give you one. All right, so now that we know about negation, we can learn three things. We're going to learn the converse, the inverse, and the contrapositive of original statement. So I know those seem like fancy terms, but don't worry about it. They're pretty easy to learn. So let's say you have a statement, if I feel well, then I will ride my bike. If I feel well, then I will ride my bike. The converse of that is when you switch the hypothesis and conclusion. So this part goes over here, and this part goes over here. Let me make that bigger. This part goes over here. Do you understand? It's just when you switch the hypothesis and the conclusion. So, in fact, I'm just going to keep those colors there, actually. No, I'm going to take them away. So that's pretty easy to learn. You just switch the hypothesis and the conclusion. I'm going to make this green, that green, and I'm going to bust out my purple color. There we go, so you can see what's going on. All right, so now let's go to so that's pretty easy. We'll give some more examples later on. So now let's go to the inverse. So you have the original statement. This is the original statement. The inverse is when you negate both the hypothesis and the conclusion. So let me tell you what I mean. Again, negate means you say the opposite thing. So I feel well, that changes to if I don't feel well. And I will ride my bike changes to I will not ride my bike. So you have to negate both the hypothesis and the conclusion, and that's the inverse statement. So if I don't feel well, then I will not ride my bike. That's the inverse. All right, let's go on to the contrapositive. And I know what you're thinking. You're thinking, there's too many terms here. This is confusing me. Well, you only have to learn three of these: the converse, the inverse, and the contrapositive. The most common one that you're going to learn, you're going to use in the real world, is the converse. But we have to learn these other ones too, because geometry books require us to know these. So the contrapositive is when the hypothesis and conclusion are switched and they're negated. So I feel well, it goes down here, and I will ride my bike goes here. So we're switching them like the converse, but we're also negating them. So if I feel well changes to then I will not feel well. Okay? And I will ride my bike changes to I don't ride my bike. All right, so there's negation and switching. So if I feel well, then I'll ride my bike changes to if I don't ride my bike, then I will not feel well. So again, I know that seems pretty complicated, but it's okay. Why don't you go ahead and take screenshots of these pages right now so you can go back and reference that. So now we're going to write the converse, inverse, and contrapositive of the following statements. If Bill runs, then he will sweat. So let's do the converse. The converse just switches the hypothesis and the conclusion. So we say, let's see here, converse. If Bill sweats, then he will run. And don't be afraid to add some words, because sometimes you have to add words in order for the sentence to make sense. All right, so that's the converse. And now we're going to do the inverse. We're gonna go back to the same order. We're gonna switch them back, and we're just gonna negate both statements. If Bill does not run, then he will not sweat. All right. Now that one makes a lot of sense. Some of these are correct. Some of them are actually false. And some of them are kind of neutral. Some of them don't really make a lot of sense. Like this one doesn't make much sense. It's kind of neutral there. All right, now we're going to do the contrapositive. We're going to switch and we're going to negate. So we're going to switch them. The sweat is going to come first. So if Bill, and we're going to negate, so does not switch, or does not sweat, then he will, and we're going to negate the second statement too, will not run. Now you're probably thinking some of these don't make any sense. Well, they don't have to make sense. We're just learning how to do the converse and inverse and contrapositive. So don't worry if they don't make sense. They don't have to. And I forgot to put my N there. All right, so now let's do number 34. See if you can do number 34 on your own. And when you come back, we'll do it together. All right, we're back. So first we're going to do the converse. And we just switch them. If an angle, now again, you can add your words to make the sentences make sense. If an angle is a right angle, then its measure is 90 degrees. So that's the converse. We switch the hypothesis and the conclusion. Now we have to find the inverse. So again, with the inverse, you go back to the original statement and you negate both of them. If the measure of an angle is not 90 degrees, then it is not a right angle. And that actually seems to make sense. So that's a statement that actually makes sense. Again, some of these make sense, some of them don't. Some of these statements make sense. Some of them don't. Contrapositive. So we're going to switch them and negate them. So if an angle is not a right angle, then it is not, or its measure, you always have to say measure of the angle, is not 90 degrees. All right. All right, so if you got those answers, good job. All right, now we're going to go to equivalent statements. Equivalent statements are two statements that are either both true or both false. So what that means is the two statements are always both true or they're always both false. So I know what you're thinking. You're thinking, well, what in the world does that mean? Well, let me give you an example here. An original statement and the contrapositive are equivalent statements because they both have to be true or they both have to be false. For example, if a polygon is a square, then it's a quadrilateral. Now that's a statement which is actually true. If it's a square, it has to be a quadrilateral because a square has four sides and that's what a quadrilateral is. Now let's do the contrapositive of that. We switch them and negate them. If a polygon is not a quadrilateral, then it is not a square. That makes sense too. If it doesn't have four sides, it surely can't be a square. So because these two are both true, we can see that that goes along with the definition of equivalent statements. So an original statement and its contrapositive are equivalent statements. That's always true. It's also true that the converse and the inverse are always equivalent statements. So here's an example. The converse of this original statement is if a polygon is a quadrilateral, then it's a square. Now that's an example where that's false. But it turns out the inverse, if the converse is false, the inverse always has to be false also. That's why these are equivalent statements. So let's see if the inverse is false. If a polygon is not a square, then it is not a quadrilateral. That is incorrect because it's possible for a quadrilateral to not be a square. For example, a parallelogram, or we could use a trapezoid. A trapezoid is not a square, but it's still a quadrilateral. So it's not true that if a polygon is not a square, then that proves that it's not a quadrilateral. So we came up with counterexamples to prove that both of these are false. Because both of these are false, and they're always either true or false, that means that the converse and inverse are equivalent statements. All right, so we don't really need to know much about equivalent statements, but that's just something to keep in mind. All right, now we're going to go on to biconditional statements. A biconditional statement is a statement in which the converse is true as well as the inverse. So let me give you an example. If the sum of the measures of two angles is 180 degrees, then the angles are supplementary. They're supplementary angles. Now the converse of that is true also. If two angles are supplementary, then the sum of their angles is 180 degrees. It turns out that because this is actually a definition, it's always going to be, definitions are always biconditional statements, meaning the original statement and the converse, they always work. Now because these statements are both true, the original statement is biconditional, and we can combine them and use the phrase if and only if. If and only if is used for biconditional statements when the original statement and the converse are both true. So now we can combine these two statements with if and only if to make a biconditional statement. Two angles are supplementary if and only if the sum of their measures is 180 degrees. So all that if and only if means is that the converse of the statement is true also. All right, so you might want to take a screenshot of that because we're going to do some problems now to practice with biconditional statements. Determine whether the following statements are biconditional, and if so, write them in if and only if form. If they're not biconditional, explain why. So number 35, if an animal is a dolphin, then it has flippers. All right? So if an animal is a dolphin, then it has flippers. So that original statement is true. Okay? But we need to figure out if the converse is true, because we want to figure out if this statement is biconditional. So we have to look at the converse. The converse of that statement, we flip the hypothesis and the conclusion, or we switch them, and then we say, if an animal has flippers, then it's a dolphin. Well, you can see immediately that that's not true, because there's a lot of animals that have flippers, like whales have flippers, but they're not dolphins. They might be mammals, and they might have characteristics the same, but not all animals with flippers are dolphins. So the converse is not correct. So we can just say not biconditional. Let's see. So we can just say whales have flippers. If you said something like that, that's good enough. All right, so again, the converse is not true. So now it's time for you to try a problem. Try 36, do your best job, or your best, and when you come back, we'll do it together. All right, we're back. So if two polygons have the same size and shape, then they are congruent. All right, so that's true. So now let's see if, and remember, the original statement has to be true also. Sometimes the original statement is going to be incorrect. If the original statement is false, then obviously it can't be biconditional. So both the original and the converse have to be true. So now let's look at the converse. If two polygons are congruent, notice how I added the word polygon, that's okay. You got to add words so you can make the grammar and the sentence make sense. If two polygons are congruent, then they have the same size and shape. That is correct, because again, this is just the definition of a congruence. So because the converse and the original statement are both true, they're biconditional. They're biconditional. And we can write in if and only if form. So two polygons are the same size and shape if and only if they are congruent. And you can say it the other way too. You can say two polygons are congruent if and only if they have the same size and shape. It's the same thing. All right, so if you got that answer, good job. All right. On to number 37. So again, determine if this statement is biconditional. Determine if the original statement is true and the converse, they both have to be true, and then you can write in if and only if form. And if they're not biconditional, explain why. So try 37, and when you come back, we'll do it together. All right, we're back. So if x over 2 plus 3 is equal to 4, then x equals 2. If x equals 2, then x over 2 plus 3 equals 4. So the converse is correct. So they are biconditional. Because if this is true, then this is true, because if x is 2, then the equation works. So biconditional, and we can say x over 2 plus 3 is equal to 4 if and only if x is equal to 2. So we got that answer. Good job. All right, try number 38, and when you come back, we'll do it together. All right, we're back. If Bill's bicycle has a flat tire, then he cannot ride today. So let's look at that's true. Obviously, if he has a flat tire, he can't ride, but and it's assuming that he can't fix it, of course. But is the converse true? The converse is if Bill cannot ride today, then he has a flat tire. The converse is not really true because it's possible that he can't ride just because he's busy. You know, he might be busy doing something else. It might not be that he has a flat tire. So the converse doesn't really make sense. So this problem is a little iffy because the original statement can be modified a little bit, but that's no big deal. So we're just going to say that the converse is not true. Bill might be busy, so we'll just say not biconditional. Not biconditional. So that wasn't really a detailed explanation, but I think you get the point. These are just some problems to get you for you to get a feel of what's going on here. All right, so look at the original statement and the converse of 39 and see if they're both true or if one of them is false. When you come back, we'll do it together. All right, we're back. If x is less than 4, then x is less than 10. Well, that's true. Let's look at the converse. If x is less than 10, then x is less than 4. Well, that's not true. Because if x is less than 10, that means that x could be 9. Okay, so that this doesn't prove that this is true. Because if x is less than 10, if that's true, x could be 9, but 9 is not less than 4. So the converse is not true, so we'll just say not biconditional. And we have to explain why. I guess we can use colons. If x is 9, then it's not less than 4. So that explains why the statement is not biconditional. All right. So if you got that answer, good job. Now we're going to learn how to write conditional statements with symbols. You need to be aware that the statement if x then y can be written with an arrow. This means if x then y. So that's just condensed notation. And negation is written with a squiggly line. So if you want to say not x, then you just put a squiggly line in front of it. So let me demonstrate. So the original statement is if x then y, and the converse would be if y then x, and the inverse would be if not x then not y. So you got the squiggly line that means not, and the contrapositive would be if not y then not x. And if you want to use condensed notation for a biconditional statement, you would use an arrow, a double arrow. That means if x, if and only if y. X if and only if Y. All right, so now we're ready to go on to deductive reasoning, because some of you might be thinking, when are we going to get to deductive reasoning? Well, again, inductive reasoning is when you take specific examples and find a pattern and then make a conjecture based on that pattern. Deductive reasoning kind of goes in the opposite direction. It uses general ideas that are always true, like theorems and postulates and logic and definitions. So you go from the general and then you come up with a specific principle or a specific conclusion based on those concrete definitions and postulates and theorems and logic. So again, the inductive reasoning goes from specific to general, and deductive reasoning kind of goes in the opposite direction, from general to specific. So we're going to start out with some examples of deductive reasoning just using basic logic. We're going to get to theorems and postulates and definitions later on. For now, we're just going to use some examples with logic and give them names. So the first thing we're going to do is the law of detachment. If x then y is true, and x is true, then y must be true also. So let me give you an example of that. That's kind of complicated. It sounds kind of complicated. So if I hurt my arm, then I will not be able to pitch in the game tomorrow. All right? So let's say that that's true. If it were not true, then you might say, well, I could hurt my arm, but I could still pitch. Then it would be not true. But let's just assume that it is true, and that generally is true. If a pitcher hurts his arm, obviously he's not going to be pitching in the game, right? So let's just assume that this is true. All right, just like we're assuming that this is true. So if I do hurt my arm, I'm not going to play in the game. That's true. So if it is true that an injury to my arm will prevent me from playing the game, and it's also true that I hurt my arm, that my arm has been injured, and that's this part, if the hypothesis is also true, if it's true that an injury will prevent me from playing in the game, and it's also true that I injured my arm, then the conclusion must be true. Now I know what you're thinking. You're thinking that's obvious, isn't it? Well, yeah, it actually is pretty obvious. This is one of the most basic forms of deductive reasoning, the law of detachment. That's just basic logic. So if an injury will keep me out of the game and I got injured, then I'm going to be out of the game. I was thinking of another example of that. If rain will cause me to bring my umbrella, and it is raining, then I'm going to bring my umbrella. That's the law of detachment. It's very simple. But we use this condensed notation to show it. All right, so now we're going to go to the law of syllogism. The law of syllogism, in my opinion, is a little easier to understand. If x then y is true, and y then z is true, then x then z is true. Now that sounded kind of complicated, but when you see an example, you'll see it's actually pretty easy. So here's an example of the law of syllogism. If I lose my car keys, then I will be late to the party. If I'm late to the party, then the host will be angry. We use this type of logic all the time. So if I lose my car keys, then I will be late to the party. If I'm late to the party, then the host will be angry. Therefore, the law of syllogism says, if I lose my car keys, the host of the party will be angry. Do you see that? So the law of syllogism says that we can make this conclusion based on that logic we used previously. So let me give you another example in case you didn't catch that. Let me give you an example in your own life. You might say, if I play too many video games, then my parents will get angry. If my parents get angry, then they're not going to let me ride my bicycle. Therefore, if I play too many video games, I won't be able to ride my bicycle. This is the type of stuff that you're going to use all the time in your life. Another example is you might say, if my parents, let's see, if I don't read books, I won't learn. If I don't learn, I won't get a job. Therefore, if I don't read books, I won't find a job. I jumbled up the words there, but basically you get the point. The law of syllogism is very easy. We all use the law of syllogism in our everyday lives. So now let's do some practice problems. Determine if the law of detachment or the law of syllogism can be used with the following statements, and if they can, make a valid conclusion using one of the laws. So again, these laws help us to come up with conclusions. If x then y is true, and if x is true, our conclusion is y must be true. If x then y is true, and y then z is true, then if x then z must also be true. I don't think I was using the if in those statements, but I meant to use if. So this is the conclusion that we're going to come to. So why don't you go ahead and take a screenshot of these laws of logic so you can use it with these practice problems. So we're going to figure out if you can use the law of detachment or the law of syllogism. All right, if 1 minus 5x equals 11, then x equals negative 2. If x equals negative 2, then Cynthia got the right answer on one of her test questions. All right, so what do you think this would be, the law of detachment or the law of syllogism? Look on your screenshot there. Pause the video. When you come back, we'll do it together. All right, we're back. So this is going to be the law of syllogism, because we have if x then y, and if we have if y then x, so therefore we can make a conclusion, and the conclusion is going to be if x then z. We can't really use x because we have x in this actual problem. So if 1 minus 5x equals 11, then Cynthia, and I'm just going to abbreviate, Cynthia got the right answer. We're running out of time, so I'm not going to say the full sentence, but you get the point. All right, I want to rectangle these. All right, on to number 41. Go ahead and try number 41, and when you come back, we'll do it together. All right, we're back. If it rains, then I will wear my coat. If I wear my coat, then I will sweat. So this is the law of syllogism. Because we have if x then y, and if y then z. So that's the law of syllogism. So then we can make the conclusion, if it rains, then I will sweat. Again, we use this type of logic every day in our lives. It's very simple deductive reasoning. All right, so if you got that answer, good job. Try number 42, and when you come back, we'll do it together. All right, we're back. If the measure of an angle is 180 degrees, then it is a straight angle. The measure of angle A is 180 degrees. So that is the law of detachment. Let's spell that out. Right, and the conclusion we can make. So if x then y is true, and x is true, then y must be true. So the conclusion that we can make, if this statement is true, and this statement is true, then the conclusion we can make is that angle A is a straight angle. Another example is if I make my parents angry, then I can't play video games. If that's true that I can't play video games, if I make my parents angry, I can't play video games. If that's true, and I make my parents angry, that proves that I'm not going to be able to play video games. Again, that's the law of detachment. All right, on to 43. So we're pretty much done at this point. We're just going to do some additional problems just to make sure that you got this stuff before you do your homework. All right, so now we're going to make a conjecture using inductive reasoning. So Daniel failed his first 3 physics exams. So it's pretty obvious that what the conjecture is going to be based on the pattern. So what would the conjecture be? Pause the video, try it. When you come back, we'll do it together. All right, we're back. So the conjecture is Daniel will fail the next exam. That might not be true, but based on the pattern, that's the logical conclusion. We shouldn't discount the boy, but again, we're using inductive reasoning. So that's the conjecture. And now we're asking, why is it possible that your conjecture in problem 43, the previous problem, why would it be possible that would be false? So try 44. Try to explain that. When you come back, we'll do it together. All right, we're back. Daniel could study hard and pass his next exam. That is possible. Remember, inductive reasoning is flawed because it's based on limited information. We don't know everything about Daniel. He could do some things that they would surprise us. Conjecture is flawed. It has the ability to be flawed. So inductive reasoning is not as strong as deductive reasoning. It's important to understand that. All right. Find the next numbers in the sequences. Try 45, and when you come back, we'll do it together. All right, we're back. We're just adding 7 each time, so the next number is going to be 26. So if you got that answer, good job. Try part B, and when you come back, we'll do it together. All right, we're back. So it looks like you're subtracting 98 every time. So if we take negative 44 and we subtract 98, we'll get negative 142. So that one, if you get your calculator out on that one, that's okay. All right, disprove the following statements with counterexamples. All planes use jet engines. Come up with a counterexample that disproves that. When you come back, we'll do it together. All right, we're back. All right, some planes they use propellers. Some planes use propellers. So that disproves the idea that all planes are jet engines. Some planes have engines that use propellers. All right, now try part B, and when you come back, we'll do it together. All right, we're back. Pizza is always made with pepperoni. So some pizzas have only cheese. So that's a counterexample. It's not true that pizza is always made with pepperoni. Or maybe we should say cheese only instead of only cheese. That's probably better grammar. All right, part C is a little more difficult, so be careful with that one. It's kind of tricky. See if you can come up with a counterexample for part C. And when you come back, we'll do it together. All right, we're back. If x squared equals 49, then x must be 7. Notice it says it must be 7, but there's a counterexample for that. If x is negative 7, then doesn't that work too? Negative 7 to the second power, that's negative 7 times negative 7. I'm just going to write it out because a lot of students forget this. That would be 49, and that works also. So x can be negative 7. That's a counterexample. So we disproved that statement. All right, on to 47. Convert the following statements to if-then form. So we're just practicing converting a statement to if-then form. Try 40. Well, we'll just do 47 together. All birds have feathers. If a creature is a bird, then it has feathers. All right, so we put it in if-then format. All right, so why don't you try 48? Put it in if-then form, and when you come back, we'll do it together. All right. If x is equal to 10, then x is greater than 6. All right. So you got that answer. Good job. All right. Identify the hypotheses and conclusions in your if-then statements above. A hypothesis is just the plural of hypothesis. So the hypothesis in this problem, what would that be? Well, if you said a creature is a bird, then that's correct. Or we can say the creature. Or we can just say a creature is a bird. That's the hypothesis. And the conclusion, what would that be? It has feathers. So if you gave those answers, good job. That's for number 47. Now let's do the hypothesis and conclusion for 48. Go ahead and try that. And when you come back, we'll do it together. All right, we're back. The hypothesis is x is equal to 10. And the conclusion is x is greater than 6. So if you got those answers, good job. All right. So number 50, we're going to write the converse, inverse, and contrapositive of this statement here. So this is good practice. I don't know how much time we're going to have here. We're running out of time. I don't want to go much longer. But see if you can try number 50. Write the converse, inverse, and contrapositive of the statement above. And when you come back, we'll do it together. All right, we're back. So start with the converse. If a bird can fly, then if a bird can fly, then it has wings. All right. That's the converse. And then the inverse. If a bird does not have wings, then it cannot fly. All right, so we just negated everything. Let me shrink that. And finally, the contrapositive. So we know a switch and negate. So if a bird cannot fly, then it doesn't have wings. And again, remember that some of these statements are ridiculous. Some of them are false, some of them are true. So if you got those answers, good job. So part B is determine the truth value of each statement above, including the original statement. So the converse, let's start with the original. So original, let's see if that is true or false. So if a bird has wings, then it can fly. Is that true or false? Well, if you know anything about turkeys, I don't think, if I remember correctly, I don't think turkeys can fly. Maybe they can. I don't remember that, but I know ostriches don't fly. So I think there's quite a few birds that have wings that don't fly. So we know that that's false, because I know ostriches, they can't fly. All right, and so that's the original statement. The converse, if a bird can fly, then it has wings. I would say that's definitely true, because if it doesn't have wings, it's not going to fly. So that's true. And what about the inverse? Remember, the converse and the inverse are equivalent statements. So if the converse is true, the inverse has to be true also. The inverse is, if a bird does not have wings, then it cannot fly. So that's true, obviously. These two are both going to be either true or they're both going to be false. Now, because the original was false, we know the contrapositive has to be false also, because again, the contrapositive and the original, they are equivalent statements. So we don't really even have to read it, but just to show you, just to demonstrate, we're going to go ahead and read it. So the contrapositive, if a bird cannot fly, then it doesn't have wings. If a bird cannot fly, then it doesn't have wings. Well, that's not true, because ostriches cannot fly, but that doesn't prove that they don't have wings. You know, ostriches do have wings, but they can't fly. So that's false. All right, so on to part C. Is the original statement biconditional? Well, the original statement was false. In order for the original statement to be biconditional, the original has to be true and the converse has to be true. But because the original was not true, it's not biconditional. So not biconditional. And the reason is the original statement is false. All right. So I don't think we have much time to continue these problems. We didn't get to these last problems. But that's okay. I think you have done enough. Now, if you'd like to take screenshots of the work we did today, you can go ahead and do that now. And you can use these screenshots to help you with your homework. or to study for tests. And this is the page that we didn't really get to. There was only one part of a problem. Alright, so now let's look at the homework. Take a screenshot of the first pages of the homework and the third and fourth page, and notice I give you all the answers. Your homework needs to be complete, it needs to be neat, it needs to be correct, and you need to know where it is. Make sure you put that homework in chronological order. So the first class and second class and third class, they need to go at the front of your binder, and this class is going to go right in chronological order. There's going to be the next page over. So get that homework done, and remember, if you don't do the homework, it's a 100% guarantee that you're going to learn absolutely nothing in this entire class. So that said, I'll look forward to seeing you in the next class.